Alright, in this video we define the sine and cosine functions based on the complex plane, and also we define the polar form of complex numbers. Okay, let's start. Okay, so let's define sine and cosine, actually cosine and sine maybe. So let u be any complex number with absolute value of 1. And let the principal argument of u be theta. Okay. So that means if we plot this on the complex plane, this u resides on the unit circle centered at the origin. Unit circle means a circle of radius of 1. Okay. So u could be anywhere on this circle. Let's say u is somewhere here. Then the principal argument is theta. Now, cosine function from our real numbers to real numbers and sine function from real numbers to real numbers are defined as follow. So cosine theta, this theta is the argument, is defined to be the real part of u. Okay, real part. And sine theta is the imaginary part of u. That's it. Very easy. So on this plot, it means this x-axis, so real coordinate, corresponds to cosine theta, and this corresponds to sine theta. Okay? And you know, this theta can be anywhere here. So in this specific particular example, it's in the first quadrant, but it can be anywhere on this unit circle. Okay, and the angle is measured from the real axis. Okay, so another example. If u is somewhere here, okay, then theta should be this. Okay, in that case, the real part is negative and the imaginary part is positive. So cosine is negative and sine is positive. So as you can see, when theta is equal to 0, then cosine 0 is here, 1, right? And cosine 0 is 1. And sine 0 is 0, because the imaginary part is 0 here. Okay, if u is here, that is when theta, the principal argument is pi half, then the real part is 0 and the imaginary part is 1. So cosine pi over 2 is 0 and sine pi over 2 is 1. Okay, what about this? When the principal argument is pi, then cosine pi, as you can see, it's negative 1, and sine pi is 0. And you should try to find the values of sine and cosine for these angles using this unit circle. So even if you forget, you know, the values of these important values for cosines and sines for important angles, you can guess from this figure. Okay. For example, what about, you know, this, if this is 45 degrees? That means pi over 4. What is cosine pi over 4 and sine pi over 4? You can guess from this figure. Okay, because this is unit circle, the length is 1. Because it's 45 degrees, this length and this length should be the same. So from that, maybe you can guess. And also from these pictures, you can see that cosine negative theta is equal to cosine theta. And sine negative theta is equal to negative sine theta. Why is that? Draw the picture. Okay. So if theta is this, then negative theta means, we measure the angle from the real axis. So if theta is this, then negative theta should be this. It's a mirror image around the real axis. So negative theta is this. So the x or the real part doesn't change, but the imaginary part will change the signs, right? So therefore, the real part doesn't change. So cosine negative theta should be equal to sine theta, and sine negative theta. So this is the sine negative theta, and it should be the negative of sine theta, right? And of course, if the argument of u where and u has a magnitude of 1, then u can be written as, just by definition, cosine theta plus I sine theta, right? Because this is the real part and this is the imaginary part, by definition. Okay, now let's prove some trigonometric identities. Okay, suppose alpha and beta are real numbers, angles. Then we have cosine of alpha plus beta equal to, I guess you have learned this somewhere in high school. So cosine alpha plus beta is cosine alpha times cosine beta minus sine alpha times sine beta. And sine alpha plus beta is equal to sine alpha cosine beta plus cosine alpha times sine beta. So let's prove this. Okay, so let's define u as cosine alpha plus I sine cosine alpha plus sine I sine alpha, and v as cosine beta plus I sine beta. Okay, then by definition of cosine and sine, we can easily see that absolute value of u is equal to the absolute value of v, which is equal to 1. So both have the length of 1. Okay, so let's draw a picture of this. Of course, we don't specify exact values of alpha and beta, so it can be any values, but let's just say alpha here and beta here. Okay, they are on the unit circle. Okay, and here on the left hand side we have alpha plus beta. So if we add these two angles, alpha and beta, maybe we have somewhere here. So that should be alpha plus beta. Okay, now as we have seen in a previous video, multiplication by a complex number with modulus of 1 corresponds to rotation by its argument. Okay, so and in this case the argument of u is alpha and the argument of beta is argument of v is beta. So if we multiply u by v, then v is rotated by the argument of u, that is alpha. Okay, so uv. So v is rotated counterclockwise by alpha. So that's what we have. So that means and also, multiplying by u doesn't change the magnitude, the modulus of v. So this one is equal to, so the modulus of product is the product of moduli. So this is still 1. Okay, so the result is still on the unit circle. That means we can write as cosine of, the argument of this is obviously alpha plus beta. So the real part should be cosine alpha plus beta. And the imaginary part should be sine alpha plus beta. Okay. Now, but we have this. Okay, so just substitute this right-hand side to this. So that will be cosine alpha plus I sine alpha, and cosine beta plus I sine beta. So that is, so cosine alpha cosine beta and minus sine alpha times sine beta. So this is the real part. And the imaginary part will be sine alpha cosine beta and sine alpha cosine beta and cosine alpha sine beta. Okay, now compare the real part with the real part and the imaginary part with the imaginary part. Then we can see that cosine alpha plus beta, the real part, is equal to this. Cosine alpha cosine beta minus sine alpha sine beta, and the imaginary part, sine alpha plus beta, is this. Beta plus cosine alpha sine beta. And we are done. So try not to memorize this formula. Okay, you don't have to. It's obvious from this argument. So, you know, if you try to memorize this, you will eventually forget. But even if you forget, if you understand the meaning of this formula, so it's multiplication of between complex numbers, and multiplication by complex number corresponds to rotation in the around the origin, counterclockwise, then you can immediately derive this formula. So should be easy. Anyway, that's it. Next, as an application of this formula, we prove the following theorem that's called de Moivre's formula. That is, for any natural number n, we have cosine theta plus I sine theta to the power of n equals to cosine n theta plus I sine n theta. Okay, maybe you can see the meaning of this immediately. Okay, let's say u is cosine theta plus I sine theta. Okay, so u squared is, of course, u times u. So that means we rotate u by the argument of u itself. Okay, so that means the argument will result in 2 theta, because argument of u is theta, and we rotate by theta again. So the argument of this is 2 theta. So that should be cosine 2 theta plus I sine 2 theta. Okay, and similarly, if you cube u, then that is u times u squared. And the argument of u squared is 2 theta, and that is rotated by the argument of u again, that is theta. So the result should be cosine 3 theta and I sine 3 theta, and so on. So we can continue this for any number of powers. So un should be cosine n theta I sine n theta. Okay, basically this is the proof. So if you are convinced with this argument, then just fine, you can move on. But anyway, let's prove this more formally using mathematical induction, just for the sake of practice. Okay, so let's prove by mathematical induction. Okay, when n is equal to 1, then the left-hand side is, it's just cosine theta plus I sine theta, which is just equal to, right away it's equal to the right-hand side, so it's okay. Suppose the formula holds for, let's say, n equal to k. Then we have cosine theta plus I sine theta to the power of k equals to cosine k theta plus I sine k theta. Now, if we multiply both sides by this, okay, then we have, on the left hand side we have this, okay, and cosine theta, so we multiply both sides by cosine theta plus I sine theta. So the right hand side becomes sine theta times this thing, okay, cosine k theta plus I sine k theta. Okay, and let's expand this one, and cosine theta cosine k theta, and the real part is sine theta sine k theta plus I sine theta cosine k theta plus cosine theta sine k theta. And using previous formula we have just proved above, then this should be equal to cosine theta plus k theta plus I. So this one is equal to this one, and this one is equal to sine theta plus k theta. But of course this is cosine, so just factorize theta. We have k plus 1 theta, and maybe we should use curly brackets, and sine k plus 1 theta. So this formula also holds for n equal to k plus 1. Therefore, by induction, we have proved the formula. We're done. Okay, so for any complex number, as long as it's non-zero, we can decompose, so to speak, this complex number into its modulus and its complex part with a modulus of 1, right? And so this part, this second part, has the absolute value of 1. Therefore, we can write this part as in terms of cosine and sine. Cosine theta plus I sine theta. So there exists some theta such that we can write like this. So that means any complex number can be written in terms of the product between its length or its absolute value and this part. So the part on the unit circle. And if we put r equal to the absolute value of z, then we can write any complex number in terms of positive or non-negative real number, r times cosine theta plus I sine theta. It's ugly. It's sine theta. Okay. So any complex number can be written in terms of real part and imaginary part, or length part and the argument part. Okay. This form is called polar form of the complex number. Okay. So complex number can be either written in this way or this way. So in this way, on the complex plane, we specify the real part and the imaginary part, right? A plus IB. In this form, we specify the distance from the origin, that is r, and the angle from the real axis, that is theta. So there are two ways to express the same thing, either by coordinates or by distance and angle. Okay, let's see a few examples. Suppose we have z equals to square root of 6 plus square root of 2i. So this is the real part, and this is the imaginary part. So first, let's factorize this. In order to do that, let's express this in terms of the polar form. And this one is, so square root of this squared plus this squared, that is 6 plus 2. That is square root of 8. That is, 2 times square root of 2. So z is 2 times square root of 2, and this one, the original form, divided by this. Okay. So this should correspond to the distance part or radius part. Okay. And this one, let's simplify this a little bit. So square root of 6 divided by this thing is square root of 3 over 2. And this one is 1 over 2i. Okay. So this one, let's plot on the unit circle. So this is somewhere here. Square root of 3 over 2, and this is 1/2. Okay, and this angle is actually pi over 6. So we can express this in this way: cosine pi over 6 and I sine pi over 6. And next example. Let's say we have a complex number z in the polar form as r times cosine alpha plus I sine alpha, and another complex number in the polar form s and cosine beta plus I sine beta. Okay. By the way, alpha and theta are not proper nouns. Okay. R we use usually for the radius part or distance part, and theta for angle part, but we can use any other symbols. Here we use r and alpha, and we use s and beta. Okay. Now, so if we multiply this, zw, so if we multiply this, we have rs, and this times this, and as we have seen before, this becomes cosine alpha plus beta, and I sine alpha plus beta. And what about 1 over z? What does that mean? So just calculate that. So that is r cosine alpha plus I sine alpha. So to simplify this, so we have 1 over r and multiply both numerator and denominator by the complex conjugate of this one. Then we have cosine alpha plus I sine alpha times cosine alpha minus I sine alpha. So complex conjugate. Cosine alpha minus I sine alpha. Now calculate this. We have actually sine alpha, and so that will be cosine alpha. So it's cosine alpha plus I sine alpha and cosine alpha minus I sine alpha. So that becomes cosine squared alpha. So minus I times minus I becomes 1, positive 1. So that's sine squared alpha. But what is this? It's equal to 1. See? So we are considering a unit circle. So the real part is cosine alpha, and the imaginary part is sine alpha. The distance between this point, and the origin is cosine alpha squared plus sine alpha squared. But the distance, this is this radius, which is 1 because it's a unit circle. So it's 1, and so the result is this, cosine alpha minus I sine alpha. However, remember, we have cosine negative alpha is equal to cosine alpha, and minus, sine negative alpha is equal to negative sine alpha. So this thing can be also written as 1 over r times cosine negative alpha plus sine negative alpha. Okay? So what does that mean? So multiplication by z rotates some point around the origin by counterclockwise by the angle of alpha, but dividing by z and also scaling by r, right? But dividing by z shrinks the point by this amount, by r, and rotate that point by negative alpha. Okay? So that means if we have some point and we have z, let's say this is u. If we multiply u by z, then u is rotated. Let's say this angle is alpha, and so this is rotated by alpha. U is rotated by alpha. So this will be alpha. And scaled by r. Okay. So the length becomes larger by alpha. Okay. But if you divide by z, then it's rotated in the opposite direction, and the length is shrunk by r. So that's the effect of dividing by a complex number. And also, this one is a complex conjugate of cosine alpha plus I sine alpha. So we can also write this as, let's see, 1 over the absolute value of z squared times complex conjugate of z. Okay. because maybe we shouldn't skip. So multiply numerator and denominator by r, and we have cosine alpha minus I sine alpha. So this part is the complex conjugate of z. And r squared is the absolute value of z squared. So this is what we have by taking the reciprocal of z. So next, consider the division z by w. Okay, of course this is just multiplication of z by 1 over w, so we can apply the same argument as the previous case. So this would be, of course we can write this as this, but also we can write as, in terms of polar coordinates, we have r cosine alpha plus I sine alpha. And for this one, that is 1 over s times cosine beta minus I sine beta. And so we have this and this, r over s, and this times this. We can write this as negative beta and plus negative beta here. So that becomes cosine alpha minus beta plus I sine alpha minus beta. So as we have explained before, dividing z by w shrinks z by the factor of s and rotates z in clockwise by beta. Okay, anyway, the functions like sines and cosine are called periodic. Okay, that is, since it's rotation, rotating by 2 pi has the same effect as not rotating, right? So first rotate by theta, then rotate that by 2 pi, doesn't change the effect. Okay, so in this sense, sine and cosine are called periodic functions. More specifically, in this case, cosine theta plus 2 pi k, where k is any integer, is equal to cosine theta. Okay, k is an integer, whether positive or negative. And similarly, sine theta plus 2 pi k is equal to sine theta, because rotating by the multiple of 2 pi doesn't change the values of these functions. So these functions are called periodic functions. And in this case, 2 pi k are periods of these functions. And the smallest positive period is called the fundamental period. Fundamental period. So in this case, the fundamental period is 2 pi in both cosine and sine. And more generally, if we have a function of x that is equal to x plus p, where p is any real number, then we say this function is periodic. And if p is a function, p is a period, then we also have x plus 2p is also has the same value as f of x. And any multiple of this has the same value. Because, x plus p uh, 2p is equal to x plus p, and since this is equal to f of x plus p, and this is equal to f of x. So any multiple of p, if added to x, has the same value of same functional value. So in general, these functions are called periodic functions. And let's define another trigonometric function. That is also, you should be already familiar with that, tangent x. That is defined as sine x over cosine x, where this is defined where cosine x is non-zero. Okay? Otherwise, it's not defined. You should again review when cosine x becomes 0. Okay? Drawing the unit circle. Now, this tangent x is also a periodic function. And as we have seen, sine x and cosine x both have the fundamental period of 2 pi. So what's the fundamental period of tangent x? Is it 2 pi? Actually, it's not 2 pi, but pi, and you should verify that by plotting the function of this. Okay, and finally, let's define some technical terms called even function and odd function and odd functions. So if f of negative x is equal to f of x for all x, all real numbers, then we say even f is even function. And if f of negative x is equal to negative f of x, then we call it an odd function. Okay? So cosine x, is that even or odd? As we have seen, this is an even function. Cos of negative x is equal to cos x. So its cos is even. And sine x, it's an odd function. So negative of sine x, negative x. So sine of negative x is equal to negative sine x, so it's an odd function. And what about f of x is equal to x squared? Is that odd or even? Let's try that. F of negative x is equal to, if we substitute this, negative x squared, so it's equal to x squared, which is equal to f of x. Therefore, this is even function. And what about f of x equal to negative x cubed? Is that even or odd? You should try to show that this is actually an odd function. Just try that. And what about tangent x? Is that even or odd? Or neither? And our function cannot be, it can be odd or even or neither of them. Okay, there may not be any symmetry for a given function. So this may be odd or even, or maybe not any of them. You should try to see, to decide which is the case. Okay, so that's all for this video. See you later.